Hello everybody, Daniele here. Welcome to another tutorial. Today I would like to share with you a patch I've used from time to time to model the speeding up and slowing down effects you can hear in vinyls or tape reels, only on instrumental music. So how do we do the same speeding up and slowing down on a score? Just to be very clear, what I mean is the classic effect you may all be familiar with, but let's hear it anyway. Okay, so in this case, I took the first portion of Ravel's quartet and I made a speed up during the first 4 seconds, and then a steady portion of 5 seconds, and then a slowing down of 4 seconds with some slopes. How do we do the same thing with a score instead of a sound? That's what we're gonna look into today. So let's take the first few measures of the Ravel's quartet. I have them here in a bach.roll in proportional notation. You can have whatever score you like, of course. It's important for it to be in a bach.roll, so in proportional notation, and not in a bach.score. If you have something in a bach.score and you want to apply this effect, first you need to convert it into a bach.roll via bach.score to roll, because our effect operates in a continuous representation of time. The first thing we need to do is to identify which portion of the score will be affected by the speed up and which portion of the score will be affected by the slowdown. And we can put markers in order to do that. So Shift Alt click on a point on the score and a marker is created. Same thing for the end. Shift Alt click and we add another marker. We can move them, and those two markers will identify the first portion of the score affected by speed up, then a middle portion which will stay the same, and an ending portion which will be slowed down. Let's give them to different names like TS, like time start, and TS, like time end. So the portion before TS will be the speeding up, and the portion after TE will be the slowing down. Once we have placed the markers, we need to slice the score into 3 portions according to the markers. Luckily, cage.slice does the job. By default, cage.slice operates on markers, which is convenient in our case. If we put here a bach.pick 1, 2, 3, we can actually see, if we put a bach.roll, that this is going to be the first portion of score, this is going to be the second one, and this is going to be the third one. Let's make them smaller somehow so we can see it. We have to dump the score in order to give it to cage.slice. So here we go, except this is not the third one because my patching was poor. And here we go. First portion, second portion, and third portion. Okay, now we need to keep the second portion as it is, but we need to change the first and the last portion somehow. Here, somewhere, we need to add a modification. But let's assume we have done that. If we have done that, we can then join the 3 scores together with bach.join 3 in rep 1. What does it mean? It means that the 3 scores that came out from bach.pick are now given a level of parentheses around them, which is what we need if we want to use then cage.join, with exactly the opposite of cage.slice. Why do we want to do that? Because if we now put a bach.roll, the score will be reconstructed exactly as it was. Let's zoom out to see it. Okay, this is not really surprising, of course. What we need to do now is to modify this part and this part in order to account for the speeding up and the slowing down. How do we do that? Well, first of all, we need to build a model of what it means to speed up and slow down. The best way of doing so is to rely on an article I recently wrote with a couple of friends. You already know Andrea Agostini, of course, from Bach, and Eric Maestri. You can find it in the Tenor Conference page in the proceeding, and you can download it. I will put a link in the description anyway. And once you download it, you can scroll down towards the end, and you're gonna find a section named Vinyl-like speed up of scores, which is exactly what we're doing. And the equation we need, there's actually two of them. The equations we need are this one, telling us that the rate of the reading, the speed rate, can be modeled as the logical time t sub l divided by a constant, all to the power of alpha. The logical time is the time in the source score, in the initial score, while the ending time, te, or the elapsed time, is the time in the final score, is the actual, let's say, elapsed time in the object we are creating. This constant t over line sub s is a fancy name just for the duration of the starting portion. So the duration of the speed up. In our case, it's the position of the TS marker. That's why we call it TS, by the way. So this gives us the speeding up rate, which is useful to know the transposition. Well, if you hear the speeding up and slowing down, you can hear that there's two parts of the effect we need to account for. The first part is a time stretch. It's not uniform, so it's gonna be a time warp somehow. Time is warped in order to account for the music speeding up. The second effect, even more apparent, is the transposition. As the rate goes down, the pitch goes down as well. As the rate goes up, the pitch goes up as well. And actually, the way it goes up and down is connected to the speeding up rate. The rate is exactly the transposition ratio as intervals. So if the rate is 2, an interval of 2 over 1 in frequency is an octave. If the rate is 4, an interval of 4 over 1 is a double octave, and so on. We need the speeding up rate to know the transposition. Then we also need the relationship between the logical time and the elapsed time in order to account for the time warp. And this is what the second equation gives us. The elapsed time is this constant, again, to the alpha, divided by 1 minus alpha, times the logical time to the 1 minus alpha. I haven't spoken about alpha yet, but it's actually a reshaping exponent. Basically, it tells us how fast, how steep is the speeding up curve. We can assume alpha equal to 0.5 to begin with, but any value between 0 and 1 will be okay. So what we need to do is to actually implement those two factors, the transposition and the time warp, according to the two equations I've just underlined. Let's start. In order to transpose, we can rely on cage.transp. Cage.transp shifts the pitch up or down in a fixed way. For instance, cage.transp 200. It's going to bring up all the first portion of score by one tone. That's not what we want to do. We want the transposition amount to be dependent on the logical time, so the onset of the initial score. Luckily, cage.transp has a lambda mode where it outputs the onsets from the right outlet and expects the difference in midicents as transposition in the right inlet. We can actually just apply the equation we saw earlier, and we can write a bach.eval. Bach.eval often helps us when we have to write equations and we need variables, and as we see, we will need some variables. In this case, we use the logical time, which is what comes in from the inlet, because we will connect it like this. So let's call it $F1. And we will divide this by the constant we saw earlier, which is the position of the marker TS. we will use a variable for this. Let's call it TS, just like the marker, okay? And let's take all of it and raise it to alpha. Again, let's use alpha as another variable. Right now, these variables are null. Notice that there's no hashtag, there's no dollar sign, so these variables are global, but they are null because they have not been defined yet. So if I take bach.eval and ask print ts, if I open the max window, I should see null. Suppose they are not null anyway, suppose they are filled with some meaningful values. This equation gives us the rate. Once we have the rate, we should consider it as a transposition ratio and convert the ratio into midcent. Luckily, to do so, there's an abstraction helping us named bach.r2mc, which takes a transposition ratio, an interval ratio, and converts it into a transposition value in midcent. This is actually what we need in order to create the transposition for the initial portion. Except that right now it doesn't work. It says bad name null and expression contains error because TS and alpha are not yet filled up. How do we fill them up? Well, alpha is kind of easy. We can just put bach.eval alpha equal to $f1 and put a load bang or load mass 0.5 as a starting default. We may do things more properly. We may take care of the fact that alpha should be between 0 and 1, so we can account for it perhaps. Well, it cannot be 0 exactly nor 1 exactly, so let's do something like max $f1 and 0.001. So this ensures that alpha is always at the very least 0.001. And let's put a min also 0.999. This ensures that alpha is at most 0.999 when we change it. Let's clear here the max window. Now, this settles the alpha case. Double clicking on the load mass fills up alpha with a value. What about TS? Well, TS is actually the position of this marker. How do we retrieve it? Markers are output exactly like everything else when we dump the score from the first outlet in the gathered syntax. Most notably, they have a marker. There's a marker specification in the header. So if we take bach.keys markers and put a print, forget about those two red lines. It just says that TS has not been defined yet, so there's nothing to compute, and the expression contains errors. But the markers have been output from here, this bug print, and you can see that there are two of them, and the onset is exactly the first element in the sublists. This is all we need. We need to retrieve the first element of the first sublist. How do we do that? We can use, for instance, bach.pick. And what do we pick? Well, we pick the first element of the first sublist. And let's do the same with the TE as well, with the second marker. We will need it later. We also pick the first element of the second sublist. Though these are the values we need. And now we fill up TS equal to $f1, semicolon, TE equal to $f2. Okay, now if we go, first TS and TE are filled up, and then all of this goes on, so we should be good to go. We shouldn't have any more red message in the Max console. Indeed, we don't, but we have some warnings. You see that indeed the transposition has been applied. Notes go up exactly as a vinyl goes up in pitch at the beginning, but the first note has been turned into a default one, which is a middle C. Why? Because its pitch was infinite. And it was infinite because at the very beginning the rate is 0. And 0 is not really a good number to work with when you take logarithms. And you can see that R2MC has a logarithm inside. So we end up with infinite stuff. That's not what we want. In order to prevent this, let's make sure that the beginning is not exactly 0, but almost 0. So we can put again a sort of max between this value and 0.00. Let's take a very small one, 001. So we can say that at the beginning is actually capped at 0.00001. The rate cannot go below this value. And now we have no more warnings. We have very, very low notes. It doesn't matter. We don't see them, but they're there. We can check that they're there by using click on a note and then move the selection via command and left right arrows on Mac, or control and left right arrows on Windows. And we move to the previous note, and once you get to the beginning, well, we see that the cents are minus 13,000 and counting. It doesn't matter, but it's there. It's very low, but it's there. This settles the transposition, but what about the time stretch? Well, the time warp undergoes the other formula we've seen. The second one, TE equal this value. And we are in luck because cage.timewarp is a module that performs this kind of warping of time and does it again in a lambda loop fashion by giving us the logical time here and expecting the elapsed time here. That's exactly our formula. We're in luck. So we just need to copy the equation. Again, we use a bach.eval, and it's going to be ts to the power of alpha divided by 1 minus alpha, all times the logical time, which is the incoming value, to the power of 1 minus alpha. Incidentally, notice that alpha has a capital A. This is a good policy. All global variables should have capital letters in order to prevent collisions with future functions. So TS is okay, alpha is okay. Just make sure that your variable name does not correspond exactly to pitch, because in Bell, pitches are a type. So if you use a name, say D2, well, D2 is not a good variable name. It's a low D. So in our case, it doesn't really matter. TS, TE, alpha are all good names. These are global variables because they have no hashtag and no $sign. So they're spread all across the Max workspace. We can access them anywhere. Let's see if it works. Indeed, it does. You see that the time has been warped at the beginning. Then the middle portion stays the same. And we haven't taken care of the last portion yet. But the first portion seems okay. At least it seems what we expected from it. So now, what about the last one? If we are clever enough, we should not do much more work. Because if we think about it, the ending part, the slowdown at the end, can be seen as the speed up of the reversed score reversed. Again, what I mean is that if I take the last portion of score, reverse it, speed it up, and then reverse it again, what we end up having is exactly a slowing down. If we think about this thing, we have already done most of the job because we have the speeding up part. We just need to do the reverse and reverse again at the end. How do we do that? Well, in order to perform retrogradation, cage.rev is our friend. We take the incoming score, we take a retrogradation, then we warp the time and we transpose it, exactly as we did before, because now we have to do a speeding up. And at the end, we reverse again. The only thing we have to change is the fact that TS is no longer the duration of the speeding up, which is a slowing down in this case. The duration of the slowing down is the difference between the length of the score and TE. So we need to have the length of the score somehow stored in a variable. To do so, we use the message getLength. getLength reports the length of the score from the playout. If we put a bach.print, we can see it in the max window. All we need to do is to take the length and store it into a variable. Let's call it dur. And we can do the getLength and temp together. First, we get the length and store it into a variable. Then we dump the score, retrieve the position of the markers, and perform the changes. Now, instead of TS, I can put dur minus TE. And same thing here. Dur minus TE. Once we've done that, we should be good to go. So let's save the patch. You never know. And let's getLength and dump. And indeed, this is the speeding up, and this is the slowing down. Notice that the duration of the speeding up and the slowing down portions have increased significantly. If we wanted to add a mechanism to preserve the original duration, either we remove the cage.time warp altogether, as we did before, this can work, or we can crop this speeding up at some point so that we only take the last portion of speeding up, the one that fits the duration of the starting section. And the same thing reversed for the ending portion. In order to implement this, we have to have a selection because we don't want to do that all the time. We want to have the user choose whether to do that. So let's put a gate, let's put a toggle somehow, and the gate. By default, we do not crop anything. Same thing here. And we can do that before the last cage ref. So exactly as we're thinking of this as a speeding up of the reverse. Now we have the toggle driving the gate, both gates actually. And let's say that if the toggle is off, everything is as we said. But when the toggle is on, we need to crop. What we need to do is to make sure that the processed speeding up is cropped so that only the last TS milliseconds remain. How do we do that? Cage.crops takes an incoming score and crops it from a starting point in milliseconds to an ending point in milliseconds. The ending point for us is the end. And to say the end, we can also say -1. That's the easy part. The hard part is the beginning, because we need to make sure that we start from a point so that the lapse of time between the point and the end is exactly TS. In other words, we need to take the difference between the processed duration of the speeding up and the original duration of the speeding up, which is TS, as we say. TS is our variable. So, how do we compute the processed duration? Let's get back to the article. And let's see what happens in this formula when we put TS as logical time. So when we are at the end of the speeding up portion. What happens is that TS to the alpha times TS to the 1 minus alpha can simplify, alpha and minus alpha go away, and we are just left with the TS over 1 minus alpha. That's convenient. Why? Because now we have a formula. We can say that the starting position is TS over 1 minus alpha minus TS. So the processed duration minus the original duration. Let's use a trigger to be more clear. And the same is true for the ending portion. Remember, we did the retrogradation exactly for this reason, so we don't have to think. We just have to take the same speeding up maths and plug them in. Only we need to change TS with dur minus TE and TS with dur minus TE again. That should be it. If we turn the machine on, if we turn the preservation, let's say that this is preserve. durations. If we turn this toggle on, we should have the durations preserved as the original. In order to see it more clearly, let's assign the same zoom factor to the two objects, and let's put it to, say, 50. Now, let's perform again the process. And as you see, now the starting portion and the ending portion have been cropped. This concludes the tutorial. I hope you had fun, and until next time.